All right, here we are, next to the last section that we'll do for this semester. It's called the central limit theorem. Here's a link to the video. Hopefully, you've already watched this. Here's the good thing: Section 6.5, central limit theorem, only has one thing different from what we just got done doing in Section 6.3, namely means not zero, standard deviation is not one. It's non-standard. But the one different thing is how we plug in the value on our calculator for the standard deviation. The standard deviation is going to be decreasing when we get involved in the central limit theorem. In fact, the new formula becomes the old standard deviation divided by the square root of n, and indicates the number of items of people we're talking about, the mean of these multiple items of people. So we'll see how this plays out in a few moments. Key concept in this section: we introduce and apply the central limit theorem. This fact about a distribution approaching a normal distribution as a sample size increases is great. But here's what I want to focus in on here. All right. He says the original population has a mean of mu and a standard deviation of sigma. The mean of a sample means will also have the exact same mean. We don't have to change anything. But the standard deviation becomes smaller. You're taking the original standard deviation, you're dividing it by the square root of how many items of people you're talking about. And this end value will be really obvious in a problem. All right. So as illustrated in the video that Al did, I call him Al, is that he took the heights of several basketball players and they range from 76 inches to 86 inches. And then he took all the different combinations of three basketball players, averaged out their heights, and as he put them on his number line, you can see the original data, the spread here, as opposed to taking multiple people, finding the average of, in this case, their heights. You can see how the data is a lot more bunched together. If your data is closer to the mean, then the standard deviation of this data is smaller than the original. You see the spread here, and the spread here is a lot smaller. So standard deviation decreases, and how we decrease it is we take the original standard deviation divided by the square root of n. That is the only change. You're still going to be finding areas to the right, areas to the left, areas in between. You're still going to have a lower limit and an upper limit. All right, you're still going to have a mean, which will be given to you. No change there. It's the standard deviation that's going to decrease, and you'll decrease it by division by the square root of n, and meaning how many items we're talking about. All right, so mean stays the same, and this is the new formula for standard deviation. No big deal. All right, if you were to do it in pencil and paper, which you're not, you'd have to calculate z-scores. Well, a z-score is the original score minus the mean divided by the standard deviation, but now the standard deviation is found another way. So it was kind of a pain to do a pencil and paper. Now it becomes even more of a pain because this z-score becomes a little more difficult to figure out, even though your calculator will do it. But here's something. You've got to make sure that z-score, when you get this answer, if you were doing it pencil and paper, was correct to two decimal places. Because you have to go to a table, it's set up for two decimal places. If this was calculated incorrectly, you'd have the wrong z-score, therefore you'd have the wrong area, and you'd have a mess on your hands. As far as the sample size being bigger than 30, I'm not even going to discuss it. All right. Um, no, just leave this. I should have taken this right. It has nothing to do with what we're doing. I want to complicate the issue here. Just ignore that. So here's an example. Suppose a team of biologists been studying this fishing pond, and they came up with a length of a single trout. Well, single trout, that gets back to 6'3". That's all we talked about is a single individual, a single whatever. It was one of that. All right, so we know that the mean is 10.2, standard deviation is 1.4. By the probability that the length of this trout is between 8 and 12 inches. All right, so we did this before. If we were doing it in pencil and paper, we'd have to find a z-score for 8, find a z-score for 12, He finds the z-scores. He then goes to his table. He finds that this area associated with a z-score 1.29 is this. An area associated with negative 1.7 is that. He subtracts the two, finds the area in the middle. He comes up with 0.8433. All right, so let me just kind of move this, take this and move it up. Therefore, the probability of a single trout back in 6.3 has a length between 8 and 12 inches is 0.8433. All right, so now we wouldn't have done that. We wouldn't have done pencil and paper. We would have gone to our calculator. We would have drawn our curve, 8 on the left, 12 on the right. It tells us the mean is 10.2. We know the standard deviation. And this is 6.3. That's all it was. And he came up with an answer. The calculator gives us 8.427, 6/10,000ths away. But we did a ton of these back in the previous section. All right. So now take that same problem now. Find the probability that the mean, the average of length of 5 trout. This is new now. This is my end value that I didn't have before. It was a single trout. Same idea. We want to find out the probability that the average of these 5 trout lies between 8 and 12 inches. So the means are the same. Nothing changes there. And here he actually finds the new standard deviation. You don't have to go ahead and do this work here. The calculator will take this number. If you put this in place, and where it says for standard deviation, you put this equation in, it'll do the work for you. There's no need to do it manually. It'd be crazy to do that. All right, let the calculator do all the work. Amen to that. So, we're doing it pencil and paper. We have to find a z-score. He already calculated this on his own. What happened here? Let's see. Changing that to a z-score, you get 3.49. Changing 12 to a z-score, you get 2.86. Going to your table, you find an area associated with 2.86 is that 4 decimal place. The area that's associated with a z-score of that is this. You subtract the two because you're finding the area in the middle. And there's our answer, 0.9979. You would not have to do that. All right. Probability that the average length of 5 fish is between 8 and 12 inches, 0.9979. Pretty high. But we're going to use the calculator. All right. We know our lower limit is 8. We know our upper is 12. We're going between 8 and 12. There's the mean. That hasn't changed. What has changed is how we enter in the standard deviation. There's the original standard deviation divided by the square root of n. N was, in this case, 5 trouts. And there's our answer, 1/10,000th away. This is great. And if we were in class, maybe, I'd have a problem where you would have to do it pencil and paper. But considering our situation, no, I'm not going to make it any more difficult than it has to be. This is straight out. It's 6.3 with one extra step. Not even an extra step. It's just how one of the steps is calculated. Instead of putting in 1.4 like you would have in 6.3, you're putting in 1.4 because you have multiple items divided by the square root of how many multiple items. In this case, 5 trout. And when we see what happens, this is the situation when we have the average of 5 trout. Notice how closer this graph here is, taller and narrower, which indicates the standard deviation is a lot smaller than this curve is spread out. All right, why this happens? Because we're calculating the standard deviation a little differently. All right, same problem. Well, not same problem, same topic. And once again, he brings us back to what we did in 6.3, and then, here's 6.5. We always worked with individual people, individual items in 6.3. Now we got 20, second part of this, mean of 20 selected. So an individual, we did this before. We want to find the area that's greater than 175. Using the calculator, we find a z-score at 0.1. We go to our table, 0.5398. But once again, I haven't said this in this video, but I said it a lot in the previous videos. The area that's associated with this value is to the left. You want the area to the right. So it's great to know that because in order to get the correct answer, what you're looking for, you take 1, subtract that area. So that's doing your pencil and paper. You got to be aware of that. Doing it, the calculator. Hey, you want this area from 175 to infinity, positive infinity. You know your low, you know your high. There they are. You know your mean. It's given to you. Standard deviation is 29 because you're working with an individual, just like in 6.3. All right, so 0.4588. You say, well, that's a ways away. Well, it's 14/10,000. No. All right, so doing this pencil and paper for 20, all right, which you won't have to do. You take the x-score, subtract the mean, divided by the standard deviation, which is calculated a little differently. Doing the math, correct the two decimal places, which you would have to do, pencil and paper. There's my 0.4, there's my 0.46, 0.6772. Once again, the area that's associated with 175 is from this vertical line to the left. You're looking for greater than, so taking 1, subtracting that decimal, 0.3288. Let's do the calculator. Calculator would draw my curve. I wouldn't have these two numbers. I would have these two. I could label that E99. Let's let the calculator do everything. All right, so my low value is right here. I'm going all the way out to E99. My mean doesn't change. What does change for the, seems like the 10th time I've said this, is the original standard deviation of 29 divided by the square root of n. N is the 20 randomly selected men as opposed to an individual. All right, hitting enter, 0.3218, doing your pencil and paper, 0.3288. This doesn't change. This is the only thing that's a little is different from what we just did back in 6.3. You're saying to yourself, well, how do I know? Well, you'll see a number. It won't be an individual. It'll be a number here that represents n. As I said, I may have said before, what if I label the problem central limit there? When you read the words central limit there, you go, aha, I got to divide to find that new standard deviation, pop it into the calculator. I've got to put the original standard deviation divided by this value of n here. Here's 20. All right. The probability that an individual man selected at random his weight is greater than 175 was 0.462. Probability that the average of 20 randomly selected men, their average weight is bigger, is a lot less. All right, 0.3288. And the reason is it's much easier for an individual to deviate from the mean than it would be for a group of 20. What's happening is low scores, low weights are canceling out high weights, and high weights are canceling out low weights. Everything becomes more compact. There's a less spread of data, meaning the standard deviation is smaller. You divide it by the square root of n. All right, 4 problems here. I should have done one of each, one left, one right, one in between. I think I did 2 that are right. All right, so I should have read I read the problem. I put it in bold here, 64. That's my end value. I drew my curve. We want the probability. That's the average snow. The mean annual snowfall will exceed. Exceed means bigger than. So there's my mean. There's my 80.8. Exceeds 80.8 means to the right. All right. There's my standard deviation. There's my end value. My 64. Mean isn't going to change. I want the probability of x being greater than. All right. So there's my low value right here. All right. You got to draw the curve. There's my upper value, E99. There's your 78. I mean, here's a case here where you got sigma divided by the square of n, but you can actually done this in your head. 16 divided by the square of 64, which is 8. 16 divided by 8 is 2. You could kind of calculate it, just put a 2 in there, but no big deal. You're putting in 4 numbers. Right? These 3 are given to you. I mean, thinking about taking the original standard deviation, dividing it by a number that I'm going to bold out for you. I'm wondering here. I'm wondering. Of course, you'd have to be watching this video. I can say you guys aren't doing that. So I'll leave that alone. Notice the answer is spot on. Pencil and paper or calculator spot on. The next one, you're looking for the area between 10.6 and 16.6 for 9 fish, not a single fish, 9 fish. There's your mean of 13. There's your end value, 9 fish. Suspiciously, the standard deviation, the original one is 9 as well. So you're looking for the area between. All right. Between, says between this low number and that number. There's your low, there's your high, there's your mean. And then the standard deviation is the original standard deviation, 9, that he tells me in the problem. Standard deviation of 9 divided by the square root of n, which also happens suspiciously to be 9. I mean, here's a case where you're going to take a 9 divided by the square root of 9, which is 3. 9 divided by 3 is 3. You have to, you have to put it in there. And there's my answer, 0.6731. And the correct answer is C, 0.6730. Notice there's nothing around this, all right? It's not a matter I'm asking you to be a round-off expert. I should have put in 4 numbers. Big deal. The original standard deviation divided by the square root of n. Not all that. Not all that. The last one here, I want the probability if I pick 40 different applicants, their ratings would be loan ratings, credit ratings will be bigger than 200. I'm sorry, bigger than 250. Mean. All right, so there's my mean of 200. I want greater than 215, so there's 215 to the right of 200. Greater than. All right. Oh, he says the word here above. Above 215 means greater than 250. Above certainly doesn't mean less than. Above means 215 and bigger. All right, there's my low, there's my high, there's my mean, there's my standard deviation divided by the square root of my n value, 40 different applicants. There's the original standard deviation divided by my n value. Here's a case where the calculator would have to do the whoops, it's 40 in the square. The calculator loves doing this stuff. Please don't try to figure this out separately. For what? That defeats the purpose of using a calculator. And you come up with 0.0289, the correct answer. Not close, but no, something else even closer. So that's all there is in section 6.5. It ain't nothing more. Nothing more going on. One little difference. And I'll go as far as labeling it central limit theorem. When you see that, provided you've watched this video, which I'll take you at your word, so we shall see. We'll find out next week for sure.